Okay, so real quick, let's keep going through these the laws of logs, the rules for logs. We said they're very similar, or actually just like the rules for exponents, because logs are exponents. So we know that when you multiply like bases, like right here, you add the exponents. So the way to kind of get a handle on this is remember that 100 is equal to 10 squared and 1,000 is equal to 10 cubed. So the exponent you put on 10 to get 100 is 2. The exponent you put on 10 to get 1,000 is 3. So if you multiply 10 by 3, you can add the exponents. 10 squared times 10 cubed is 10 to the 2 plus 3, which is 10 to the 5th. And so what that means is that the log base 10 of 10 squared times 10 cubed is going to be the same thing as the log of 10 squared plus the log of 10 cubed. So the exponent you put on 10 to get 10 squared times 10 cubed is the same as the exponent you put on 10 to get 10 squared plus the exponent you put on 10 to get 10 cubed, which is 5. So another way to say that would be log base 10 of 100 times 1,000 is equal to log base 10 of 100 plus log base 10 of 1,000, which is 5. That sounds complicated, but basically the general form of the product rule is log base b of mn is equal to log base b of m plus the log base b of n. So you want to make sure you don't get this backwards, because you could sit there and think, okay, log base b of m plus n is equal to the log base b of m times n, and that is not true. Okay, there are so many ways you can think about this that you get confused. But what it is if you have the log of a product, it is equal to the sum of the logs. Multiply like bases, you add the exponents. All right, so here's an example. You have log base a of 4 plus log base a of 6, which means that you're multiplying like bases. If you're adding the exponents, that means you're multiplying the like bases. So that means that log base a of 24, which is 4 times 6, is equal to log base a of x plus 4. So that means if these two logs are equal and they both have the same base, a, then their arguments must be equal. There's no other way. If you put the exponent you put on a to get 24 is the same as the exponent you put on a to get x plus 4, then 24 and x plus 4 must be the same thing. So if the bases are the same, the arguments must be the same. So x would be 20. And then when you finish finding that out, you just quickly go back, plug 20 into the equation anywhere you see an x. And if you ever get a negative argument, you know that that is not a solution. But there's nowhere you're going to get a negative argument here. The arguments are 4, 6, and now 24. And none of those is negative, so this is the solution to this equation. So, moving on. The quotient rule for logarithms comes from the rule for exponents that says when you divide like bases, you subtract the exponents. So 10 cubed over 10 squared is 10 to the 3 minus 2, which is 10 to the first. So we could write the exponent you put on 10 to get 10 cubed over 10 squared is the same as the exponent you put on 10 to get 10 cubed minus the exponent you put on 10 to get 10 squared. 3 minus 2, which is 1. So the general form of the quotient rule is log base b of m over n is equal to the log base b of m minus the log base b of n. So if we look at an equation, look at an example, you have, first of all, this log, which is a sum of two things. And so what you would say is, what you would be tempted to say is, oh, well, that's log base 4 of x times 6. No, it is not. That's not what the rule says. The rule says log base b or whatever of m times n is equal to log base b of m plus log base b of n. So be careful. When you see a sum in the argument of a log, there's no rule to help you deal with that. It's only when you see a product inside the argument of a log that you can do something about it. So here you've got inside the argument of a log, you have a sum. Nothing you can do about that. Here inside the argument for a log, you have a difference. Nothing you can do about that. That's not what these rules talk about. They talk about products and quotients inside the argument of a log. So don't get confused. All right. So here's what's going on. You're subtracting two logs that have like bases. That means you must be dividing their arguments. Okay. If you go back, here we have log base b of m over n is equal to log base b of m minus log base b of n. So if you have something that looks like this, a difference of two logs, that means you're going to divide their arguments. Okay, so the equation we're looking at right now starts on this side and therefore it equals the left side. Okay, so I have a difference of two logs. Here's the minus sign. Here's one log. Here's the other log. They have the same base. That means that this is equal to log base 4 of x plus 6 divided by x minus 1. And that's supposed to equal log base 4 of 5. And since the bases are the same, the arguments have to be the same. If log base 4 of this thing is equal to log base 4 of that thing, those two things must be equal. So x plus 6 over x minus 1 is equal to 5. Cross multiply, you've got 5x minus 5 equals x plus 6. So 4x equals 11. So x equals 11 over 4. And so you can go back and check, make sure that both arguments here are not negative when you put in 11 fourths. 11 fourths plus 6 is positive. 11 fourths minus 1 is also positive. So this is the solution. Moving on to the power rule. The power rule for logs comes from the rule for exponents that says when you raise a power to another power, you multiply the exponents. So 10 squared raised to the third power is 10 to the 2 times 3 or 10 to the 6th. The general form of the power rule for logarithms is that log base b of m to the n is equal to n times the log base b of m. All right, so here's an equation to solve. You've got log base b, 3 log base b of x equals log base b of 8. That means you can take, this is, again, it's kind of going backwards. If you have something that looks like this, which is what this is, you can rewrite it like that. So we can take that coefficient that's in front of the log and put it in the exponent of the argument. So that becomes x cubed. And log base b of 8 is what that's supposed to equal. And since the bases are the same, the arguments have to be the same. So x cubed equals 8. And we know that that would only happen if x were 2. If we go back, there's no way that's making a negative argument. So that is the solution. Over here, you've got log base 12 of x is equal to 2/3 log base 12 of 64. The left side, nothing you can do with it. It's just nothing you can change there. On the right side, you can take the coefficient of the log and put it into the exponent of the argument. So log base 12 of 64 to the 2/3 power. So log base 12 of x is equal to log base 12 of 64 to the 2/3. So the cube root of 64 is going to be 4, and square it, that's 16. Therefore, like logs, like bases, so the arguments must be the same. X equals 16, and that doesn't make any arguments negative, so it is the solution. Okay, properties of inverse functions. In lesson 32, we learned to find the inverse of a function by solving for x, and then interchanging all x's and y's. Inverse functions undo one another, which means that if you put x into one function, and then put the result into the inverse function, you'll get x back again. So if f and g are inverse functions, and you put x into the g function, get a g of x, and then you take whatever you get for g of x and put it into the f function, so f of g of x, you get x again. If you put x, this is the wrong letter here, you put x into the f function and get f of x. You take that f of x and put it into the g function, and you get g of f of x, you're going to get x back again. That's what it means for f and g to be inverse functions. They undo one another. So if you take something and do whatever the g function does to it, and then you do whatever the f function does to it, it won't change the thing at all. It'll just end up being the same as it was in the beginning. So definition of inverse functions. Two functions f and g are defined to be inverse functions if f of g of x equals x for all x in the domain of g, and g of f of x equals x for all x in the domain of f. So both things have to be true. F of g of x equals g of f of x equals x. That's when you have inverse functions. So if you look at an example, show that f of x equals 1/3 x minus 3 and g of x equals 3x plus 9 are inverse functions by computing their compositions. So f of g of x to start with. You take the f function, or you take the g of x function and put it into the f function. You're going to put that in for x. So 1/3 times 3x plus 9 minus 3 is equal to x plus 3 minus 3, which is x. So that worked. We put g of x into the f function and we got x. Now let's try the other way around. G of f of x, let's put this into this function, into the x. So 3 times 1/3 x minus 3 plus 9. So that gives me x minus 9 plus 9, which is x. So yes, both of them are true. They both come out to be x. And so f and g are inverses. F and g are inverses. All right, example 40.6 says show that f of x equals 1/x minus 3 and g of x equals 3x plus 1/x are inverse functions by computing their compositions. So we're going to do f of g of x, which means I'm going to take this function and plug it in for x into that function. So that's going to be 1 over, putting in 3x plus 1/x for x, 3x plus 1 over x minus 3. So if we multiply this whole fraction by x, we're going to get x over 3x plus 1 minus 3x, and that is going to be x over 1, which is x. So that works. Let's try g of f of x. Now we're going to take the f function and put it into the g function for x. So we're going to have 3 times 1/x minus 3 plus 1 over 1/x minus 3. So we multiply that whole fraction by x minus 3, and we're going to get 3 plus x minus 3 over 1. And that is going to give us x over 1, which is x. So that works. They are inverses. We just proved it.